Okay, this is lesson 4.5. We reached the end of unit 4, and today we're going to talk about this topic called concavity and the points of inflection. And then last day we looked at the first derivative test for finding relative extrema. Now we're going to show you something called the second derivative test to find the exact same thing. Alright? Now let's just begin with some definitions here. A graph with this shape that you see here is called concave upward, okay, or concave up. Now notice for graphs of this shape, the tangent lines always lie below the graph, okay? And look at what happens to the slope of the tangent lines as we go from left to right. Very negative, not so negative, not so negative, flat, getting positive, positive, more positive, more positive. So I hope you can see that the slopes of the tangent lines are increasing. Now, when I say the slopes of the tangent lines, that's thinking f prime, right? And when I say are increasing, that means the derivative of what f prime is, bigger than 0. So what's the derivative of f prime? Well, the derivative of the derivative is you got it, the second derivative. And so the second derivative has to be greater than 0. Now it has an equal sign here, and I'll mention the equal sign in a bit, but just understand right now that the second derivative has to be positive. Okay? Now, the next shape is concaving down, and notice the tangent lines are always above the graph, and they go from positive to less positive to less positive to 0 to a bit negative, more negative, more negative. So in this case, the slopes of the tangent lines are decreasing. So once again, the slopes of the tangent lines, which is the derivative, decreasing, that must be less than 0. The slopes of the derivative, or f double prime, then must be less than 0. Once again, I have an equal sign here, but I'll talk about that in just a few moments. Okay? Now, if you want to memorize this, instead of having this big blurb, then here's another non-mathematical memory device. Concave upward, notice it's positive second derivative. Smiley face, so here's my smiley face with my two positive signs in my eyes, yay! Concaving downward, however, second derivative is negative. Frowny face, so sad. And because I'm sad, I don't want my eyes to be open, I'm going to shut them and make them align, like that. Okay? Now, before I talk about this next topic of a point of inflection, let me make a little note about that equal sign, okay? That equal sign, why it's there. So let me give you an example of a graph, like y equals x to the power of 4. That's a graph that looks like this, right? Whee! Okay? I would say that the graph is concaving upwards everywhere because, look, the tangent lines go from very negative to 0 to positive, so notice the tangent lines are always below the graphs, and the slopes of the tangent lines are always increasing. Okay? Now, let's just quickly take the second derivative. So the first derivative of x to the power of 4 is 4x cubed. The second derivative is actually 12x squared. And notice at x equal to 0, if I were to find the second derivative at 0, that would be 12 times 0 squared, or 0. And that makes sense. Hopefully you can see. I hope that you can see. I think that makes sense because look, the derivative here is 0. Yeah. But you can say that the graph is concaving up everywhere. So that's why we actually have that including 0, because it could be a possibility that it could be 0, yet the graph is still concaving upward. Similarly, if I were to flip this around, right, y equals to negative x to the power of 4, you get the same idea where it's still going to be 0, but this is a case where it's always concaving down, and that's why we have that equal sign there as well. Okay? Many textbooks also just use greater than or less than, like this idea of positive and negative, which is perfectly fine, but I want you to be aware that equaling 0 could be a possibility as well. Okay? In some special cases. Now, one last terminology before we begin. There is something called a point of inflection, and that is true if the graph, first of all, has a tangent line at that point, and the key thing is the graph changes concavity at that point. So notice here to the right we have a graph of y equals x cubed. Woo! And notice we have here sad face concaving down, and then woo, happy face concaving up. So at 0 here, yes, we do have a tangent line, it's flat, and we do have a point of inflection because the concavity does change. Okay? Alright. So, now I'd like you to take a look at example number 1. Okay? Oh, by the way, before that, just a note here, some textbooks use other definitions for a point of inflection that do not require the existence of a tangent line. Okay? Now the AP test, though, is carefully written so that this is not an issue, so don't worry about that for the AP exam. Okay? Alright, now let's take a look at this example. I want you to try this, looking at the graph to the right, and then see if you can answer these questions based on their definitions from above. Okay? I'll give you 2 minutes. Go! Okay, I won't make the whole video go for 2 minutes. That's just too long, but I'll give you the answers now. Which intervals is the graph concave up? Did you say from -2 to -1? I agree. Concaving up. What else? Oh yes, happy face right here. From 1 to 3. And then also, yeah, from 4 to 5. Concaving down, did you say from -1 to 1? Sad face. And then how about from 5 to 6? By the way, this part here from 3 to 4, that's a straight line, right? That's where there's no concavity, so that's the part for number 3. And anywhere else where there's no concavity? Yeah, there's this part right here. I don't know if you see this as a straight line as well, but 6, 7. And so now my questions are, where are the points of inflection? Where does concavity change? It changed right here. 1, 1, right? Where else did it change? Yes. 5, 1, And if you said, let's look at this point here, I'd say, because there really is no tangent line at that point. Similarly here, no tangent line at that point, no tangent line at that point, because these are corners, and therefore we do not want to classify them as points of inflection. Okay? Now, this is a visual, but what about analytically using algebra? Well, the idea is the same as we did before with the increasing, decreasing, but this time because concavity talks about the second derivative, we're going to use a second derivative number line. Okay? So instead of drawing the first derivative number line, remember what we did there with the increasing, decreasing, now we want to find the second derivative number line. Okay? Now, most textbooks often use open intervals for concavity, but there is no universal definition of concavity, so there is some chance for ambiguity. Okay? There are a few texts out there that define concavity in terms of where the first derivative is increasing, decreasing. So the same issue arises about including or excluding the endpoints. You're like, oh no. But like I said, I think for our studies here, let's just worry about concavity with just open points or open endpoints. I think that's just the prevalent thing that you'll see out in the calculus world. Okay, so here's our next example here. Can you find the points of inflection for this lovely equation? So this time, if I'm looking for the points of inflection and then concavity, we need to find not the first derivative, but the second derivative. But of course, we need to find the first derivative first before we can find the second derivative next. First derivative, go ahead and do it. Oh, don't forget the derivative of a constant is, 0. Just checking. Second derivative then, here we go. 4 times 3, that's 12x squared. 3 times 2, that's 6x. And then minus 6. I'm going to have to make this equal to 0, right? So why don't I try to factor out something here? That's 2x squared plus x minus 1. I can factor this trinomial as well. I hope you can as well. I'm going to say 2x minus 1 and then x plus 1. This is cool because I want to do what? I want to now set the second derivative equal to 0 and solve. I'll get here x equals to 1/2 if I do. I'll get x equals to negative 1/2 if I do. Remember, we should look for where the second derivative also does not exist, but this is a polynomial, so we don't have to worry about that for this question. So I guess all we have is this point 1/2 and negative 1. Okay, so these are the possible points of inflection. We don't know if they actually are or not. But here is now where I'll go and set my second derivative number line. I'll plot negative 1. I'll plot 1/2. And then I'll test the regions. So here's one region. Here's another region. The third region. You can test by plugging in any number in each of these regions. So if I take something like negative 2 and I plug it in, what do I get? 12 times negative 2 squared plus 6 times negative 2 minus 6. That is what ugly number? 48. I think it's some big number, but I know it's going to be positive. So positive. Let's choose 0. I know that one's going to make me happy because it's always easy to evaluate 0. It's just going to be negative 6. And then thinking about it like 1, 12 times 1 squared. I think this is also going to be positive because it's positive 12, so there you have it. Knowing this now second number line, you should be able to tell me the points of inflection where it concaves up, concaves down. Let's do the intervals where it concaves up first. Concave up from negative infinity to negative 1, and also from 1/2 to infinity. Where is it concaving down? Well, that's where the second derivative is negative. Negative 1/2 to 1/2. And then our points of inflection. Okay, well, that's where the concavity changes. And both of those values where the second derivative equals 0 show me where the concavity changes. So negative 1 comma, and I'm going to leave that blank for now because I don't actually know what the y value is. Remember, these are y values, right? Points, y values. Let me write down y values. So how do I find y values? Yeah, stick it into the original y equation. And if you do that for negative 1, let's see, negative 1, I think the answer is negative 2. So I'm going to put that here. And then 1/2, 1/2 to the power of 4. What's f of 1/2? 1/2 to the power of 4 plus 1/2 cubed minus 3 times 1/2 squared plus 1. 1/16. 1/8. What is this? 3/4 plus 1. What's 1/4? I think it's 7/16. Okay. There you go. So there you have it. Okay. We've discussed the points of inflection and concavity for this graph. All right. Number 6. Same business. This time with a rational function. But this time I'm nice. I gave you the second derivative. Say thank you. So now I'll list the intervals where the graph is concave up, concave down, and the points of inflection. So same as the previous question, but this time I gave you the second derivative, so we'll just quickly set the second derivative equal to 0, and that means the numerator has to be equal to 0, and I'm thinking no such values, because everything is positive there. I can't make it equal 0. Okay. Don't forget, I also should check where f double prime does not exist. That occurs, of course, looking at the denominator. So x squared minus 4 all cubed equals to 0, or can equal to 0, I guess. So x squared can equal to 4, so x can equal to plus or minus 2. Okay. Now, these aren't actually points of inflection, okay? So note, not points of inflection. Why? Well, they're not points because They don't exist, right? They don't exist in the second derivative. Plugging in here, they don't exist in the original y value anyways. So these are not points of inflection, yet they may help me determine the concavity. So now when I graph out my second derivative number line, notice I'm going to plot -2 and 2. I like to write down just little like restrictions R. So I know it's a restriction. It's not really an actual point of inflection. I will then go ahead and test out the 3 regions. Here, here. Whoa, what happened there? That was not right. Here, I said. Here, I said. And here. Test out those 3 regions. Okay? And then when you test it out, once again, you're plugging it into the second derivative. So you can plug it in. I will plug it in. I will get you the answer. I think this one's also positive. This one's negative. This one's positive. So once again, concaving up would be the region from -infinity to -2. And also to infinity. Concaving down would be the region from -2 to 2. And once again, no points of inflection for this example. Okay, if that was too much, take a little quick break. So pause my video and then come back for the next part. But the next part's actually kind of interesting too, because I want to actually show you another way of finding relative extrema. Now, oh yeah, take a break. Okay, press pause, come back when you're done. Okay, don't go for too long. Now, the second derivative test for relative extrema really talks about second derivatives. Now, remember how we said the graph is concaving up like this, smiley face? Concaving up. And sad face, concaving down. Now, the lowest point of a concaving up graph, that would give us a, that's right, a minimum. The highest point of a concaving down graph would give us a, you got it, a maximum. So really, you don't need to do any number line anymore. Okay? The same procedure of finding the critical numbers applies to see if it's a max or min, but then to analyze if it's a max or min, all you need to do is plug in the critical numbers into the second derivative and then analyze its concavity. If it's concaving up, you got it, it's a min. And if it's concaving down, you got it, it's a max. Okay? Now the second derivative test is good in the sense that if you can get me a number where it says positive and negative, it's great. But what happens if actually the second derivative equals to 0? Well, if that's the case, sorry, you're out of luck, because we can't tell. And therefore, you probably have to go back to the first derivative test. Okay? Alright, so now let's try number 7. Use the second derivative test now to find the relative minimum and maximum for the points of this graph. So our first step once again is to, find the first derivative to find the critical numbers. So we'll find the critical numbers first. Find critical numbers first. Do that by taking the derivative. The derivative, -12x cubed plus 12x. Nice! How do we find critical numbers again? We set the derivative equal to 0. Let me factor out at -12x. I get what? X squared minus 1. Ooh, I like this. Difference of squares. Ooh, I have 3 possible x values. Wow. Okay. I can do that number line for the first derivative, but this time, wait, I told you to use the second derivative test, so guess what I need to do first? Next, find the second derivative, and then evaluate at all possible critical numbers. So, here's my first derivative. Let me quickly find the second derivative now. Negative 36x squared plus 12. Nice. Don't need to factor instead equals 0. We're not doing the inflection points and all that kind of stuff. All I need you to do now is just plug it in. So plug in 0. Plug in negative 1. And plug in 1, right? All three of these possible values. When I plug in 0, I get 12. When I plug in negative 1, I get negative 36 plus 12. That's negative 24. And when I plug in 1, I also get negative 24. What does this mean? Well, a positive number for the second derivative means concaving up. So therefore this must be a relative minimum at x equal to 0. And then these other two, since they are negative, that means it must have been concaving down like this. So these two are relative maximums at both x equals plus or minus 1. So I want the points again. So once again, what are my relative minimum points or maximum points? So let's just do the relative maximums first. That would occur at 1 comma, and how do I find the y value? Y value, y value, y value. So what would that be? Negative 3 plus 6, that's just 3. So the relative max is 1 comma 3. Okay, remember these are coordinates, so I'll say relative max point, perhaps, to make sure that we don't confuse those with intervals. And the relative minimum point would occur at 0. So that would be 0 comma y value of 0. Okay, there we have it. Using the second derivative test to help you find relative max or min. Turn the page. Oh, one more. This interesting graph. Like I told you, it's not graph, sorry. Interesting table. AP loves to give you charts with just limited amount of information. So looking at this chart, I'm asking you that g of x is a function with some derivative value shown. Okay? It says find the x values of the relative maximum and relative minimum where possible. So first of all, what do we need to do? We need to find out the critical numbers. How do we figure out the critical numbers? We set the derivative equal to 0. Great. So where is the derivative equal to 0? So let's again find the possible critical numbers. And once again, where are they? It's with a derivative equals 0. Oh, that's here, 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 and here. So your x values could be negative 3, negative 1, 0, or 2. Nice. Okay. Now, once we've done that, our next step is to now find the concavity by looking at, that's right, the second derivative at each of those values. So when x equals negative 3, the second derivative is 4. So in this case, f double prime of negative 3 is 4. That means smiley face. Okay, probably a minimum, right? Okay, how about the next one? Negative 1. Oh, sorry, it's not f, it's g, it's my fault. G double prime of negative 1, that's negative 1. Concaving down. Perhaps a maximum. At 0, let's see what happens at 0. G double prime of 0 is 0. Well, that's the one we're like, we don't know. So, remember, I said when possible. No clue what's happening at 0. And then finally at at x equals to 2, we have here G double prime of 2 being equals to 3. That must be another minimum. So ultimately now, it says find the x values of the relative max and relative min. I will say now the relative max occurs at x equal to negative 1 or x equals to 2. Right, those are the x values. Y, I'll say because, and once again you have to quote that the derivative is equal to 0, and its second derivative is bigger than 0. Okay? And then similarly, the relative minimum that occurs in this case at x equal to -3. Why? Because once again, quote that the first derivative equals 0 because that's talking about the critical numbers, and then the second derivative is less than 0. And once again, this one at 0, not good news for us. We have no idea. Alright, that's it for Unit 4. It's time for you to practice with assignment 4.5.